Earth's worst biological crises may have something important in common. The danger was not always simply that the planet became extremely hot, extremely cold, or filled with carbon dioxide. New research suggests that life was especially vulnerable when Earth was changing from one long-lasting climate state into another. Scientists examined 539 million years of geological and fossil evidence, covering almost the entire history of complex animal life. Instead of seeing Earth's climate as one continuously changing system, they found something unexpected. For tens of millions of years at a time, the planet repeatedly settled into relatively persistent combinations of temperature and carbon cycling. Then those patterns reorganized. The researchers identified 5 major climate carbon regimes separated by comparatively sharp transitions. When they compared those transitions with the fossil record, periods of ecological instability and elevated extinction repeatedly appeared nearby. In other words, Earth may have spent much of the last half-billion years jumping between a small number of planetary states, and the transitions were often dangerous for life. To find this pattern, the researchers needed something that could survive hundreds of millions of years. They turned to atoms locked inside ancient marine rocks. 2 measurements were especially important: carbon isotopes and oxygen isotopes. The relative abundance of different carbon isotopes can record major changes in the carbon cycle, such as volcanic carbon entering the atmosphere or large quantities of organic carbon being buried. Oxygen isotopes contain information related to temperature, ice volume, and ocean conditions. Neither measurement provides a simple thermometer or carbon dioxide meter by itself. But when thousands of measurements from different geological periods are combined, they create a long chemical history of the Earth system. The researchers then used a mathematical technique called recurrence analysis. Imagine recording the position of a pendulum for a very long time. Even if it constantly moves, it repeatedly returns to similar combinations of position and speed. Those recurring patterns tell you something about the underlying system. The scientists searched the geological record in a similar way. They asked when the carbon and oxygen isotope system repeatedly returned to similar conditions and when that recurring behavior suddenly changed. Instead of one continuous cloud of climate states, distinct blocks appeared. The researchers nicknamed them Haggis bins because their recurrence plots had a mottled, block-like appearance. But behind the unusual name was a serious result: 5 persistent Earth system regimes stretching from the Cambrian period to today. The oldest began around 539 million years ago. This was the early Paleozoic greenhouse world, an era when animal diversity exploded in the oceans. The Cambrian explosion produced most major animal body plans, and the later Great Ordovician biodiversification dramatically increased marine diversity. But it was not a calm paradise. The carbon cycle was highly variable, and several major extinction intervals occurred during this first regime. Geological records show repeated carbon isotope disturbances and large volcanic events. Then, approximately 447 million years ago, the system shifted. That transition coincided with one of the most severe biological crises in Earth's history. During the Endordovician mass extinction, researchers estimate that as much as 86% of recently evolved biodiversity was lost. The unusual part is what happened to climate. Instead of the classic story of catastrophic warming, Earth entered a short but powerful icehouse. Glaciers expanded, sea level dropped, marine habitats changed, and then conditions shifted again. The planet crossed from one climate carbon configuration into another. Life had to reorganize with it. The third major regime began around 358 million years ago and lasted into the Triassic. During part of this interval, enormous forests spread across the continents. Vast quantities of organic carbon were buried and eventually became many of the coal deposits humans extract today. Earth also entered the late Paleozoic Ice Age. Then the planet changed direction again. Massive volcanic provinces erupted over millions of years. Among them were the Siberian Traps, one of the largest known episodes of continental volcanism. Around 252 million years ago, Earth experienced the end Permian mass extinction. It was the greatest known biological catastrophe of the Phanerozoic. The new study notes estimates that roughly 95% of species may have disappeared. Oceans lost oxygen, temperatures rose, the carbon cycle was violently disturbed, and ecosystems collapsed. This crisis occurred near a major reorganization from the late Paleozoic world toward the warmer Mesozoic greenhouse. The important point is not that the new research replaces volcanism as an explanation. It does not. Instead, it suggests that the existing state of the planet may determine how vulnerable life becomes when an enormous disturbance arrives. Think of two houses struck by the same storm. One has intact walls, a strong roof, and dry foundations. The other already has weakened supports and water underneath it. The storm may be identical, but the consequences will not be. Earth's biosphere may behave similarly. A volcanic eruption, asteroid impact, or carbon pulse matters enormously. But its biological effect may depend partly on whether the climate carbon system is sitting securely inside a long-lived state or already approaching a transition. The researchers tested this idea by creating a measure of biosphere vulnerability. Instead of counting only the largest mass extinctions, they combined changes in species turnover with estimates of global biodiversity. This allowed them to ask whether ecosystems were systematically more vulnerable around the boundaries between major climate states. They were. Vulnerability tended to increase near regime transitions. The next major state lasted from roughly 239 to 57 million years ago. This was much of the Mesozoic greenhouse world, when dinosaurs dominated terrestrial ecosystems and warm conditions extended far toward the poles. But again, stability did not mean nothing happened. The period experienced extraordinary volcanic activity. The Central Atlantic magmatic province erupted near the end of the Triassic. Later came the Karoo-Ferrar eruptions, the Ontong Java Plateau, the Deccan Traps, and several other huge igneous provinces. The interval also contained multiple extinction episodes. Around 201 million years ago, the end Triassic extinction eliminated large numbers of species shortly before dinosaurs became dominant on land. Then, 66 million years ago, an asteroid struck what is now Mexico. The impact abruptly changed Earth's atmosphere, climate, and ocean productivity. Around 3/4 or more of species disappeared, including every non-avian dinosaur. Again, the geological record shows that biological crises occurred in a climate carbon system that was repeatedly being disturbed and reorganized. The fifth regime began roughly 57 million years ago and continues today. Earth moved away from the Mesozoic greenhouse and toward the modern Cenozoic icehouse. Antarctica became isolated as continents shifted. Permanent Antarctic ice developed. India collided with Asia. Ocean gateways changed, and eventually northern hemisphere ice sheets expanded. The modern world is therefore not simply the latest point on a smooth cooling curve. According to the new analysis, it represents another persistent climate carbon regime. And remarkably, the researchers found that fossil biodiversity during much of this recent interval appears comparatively resistant to extinction relative to several older regimes. But this is where the study becomes especially relevant. A stable regime does not mean the system cannot change. The researchers built a simplified climate carbon model containing greenhouse warming, rock weathering, ice reflectivity, carbon inputs, and other feedbacks. The model could settle into multiple stable conditions. Imagine a landscape containing several valleys separated by hills. A ball placed inside one valley tends to roll back toward the bottom after small disturbances. That valley represents a stable climate state. Push the ball hard enough, however, and it can cross the ridge into another valley. Once there, it may remain in the new state even after the original push disappears. This concept is known as multiple equilibria. The geological data appeared consistent with Earth spending tens of millions of years inside one climatic valley before moving into another. That does not mean researchers have identified 5 exact climate settings that Earth must always occupy. The geological record is incomplete. Dating becomes less precise farther into the past. Carbon and oxygen isotope records contain uncertainty, and the fossil record does not preserve every organism equally. The authors explicitly designed their analysis for large global composite datasets rather than individual rock formations. The 5 regimes are therefore a framework for understanding long-term Earth behavior, not 5 rigid switches hidden inside the planet. The research also does not claim that a new regime transition is happening today. Modern anthropogenic warming is occurring vastly faster than most geological changes represented in a 539 million-year record. The study cannot tell us an exact temperature or carbon dioxide concentration at which modern Earth would move into another persistent state. But it does provide a warning from deep time. The biosphere appears particularly vulnerable when the background climate carbon system is reorganizing. That means the speed and direction of environmental change may matter alongside the final temperature itself. A species can adapt to a warm climate. Another can adapt to a cold climate. But ecosystems can struggle when temperature, rainfall, ocean chemistry, sea level, oxygen availability, and food webs all begin changing together. Earth's largest biological crises were never caused by a thermometer reading alone. They happened when entire systems were disturbed. This new study turns 500 million years of scattered rocks and fossils into a larger pattern. The planet seems capable of remaining in one broad climate carbon state for tens of millions of years. Volcanism, tectonics, weathering, ice, atmospheric carbon dioxide, oceans, and life interact until the system settles into a persistent configuration. Then something changes enough to reorganize those relationships. And when Earth moves between those states, life often pays the highest price. The most dangerous moment may not be when the planet is hottest or coldest. It may be when the planet itself is changing what kind of world it wants to be.